Welcome to Module 8, Summarizing Virtualization and Cloud Concepts. This module covers two of the most foundational modern IT topics, client-side virtualization and cloud computing, both essential for the A+2 201-201 exam and for practically every IT role today. By the end of this module, you'll be able to summarize client-side virtualization and summarize cloud concepts. These two outcomes map to the two lessons ahead. Lesson 8.1, Client-Side Virtualization. This lesson maps to A+2 201-201 Objective 4.1, Explaining Virtualization Concepts. By the end of this lesson, you should be able to answer, what are the differences between Type 1 and Type 2 hypervisors, and which is more suitable for client-side virtualization on employee workstations? How can client-side virtualization support legacy software and provide sandbox environments for testing? And what are the key resource requirements for setting up a client-side virtualization workstation? Two more questions for this lesson. How does the amount of system memory affect virtual machine performance in a client-side setup? And how does container virtualization differ from traditional virtual machine virtualization, including the benefits of using containers? Type 1 hypervisors, also called bare metal, run directly on hardware with no host OS. Think VMware ESXi or Microsoft Hyper-V server, used in data centers and enterprise servers. Type 2 hypervisors, or hosted, run on top of a host operating system. Think Oracle VirtualBox or VMware Workstation, easier to set up on employee workstations. Client-side virtualization specifically means Type 2 hypervisors, where a workstation runs VMs alongside its normal applications. Client-side virtualization has a few common uses. Legacy software support means running an older OS, like Windows XP, in a VM to support apps that are incompatible with modern systems. Sandbox testing means creating isolated VMs to test patches, apps, or malware without risking the host system. And training and labs give employees or students a virtual environment to experiment in without breaking the production OS. Setting up client-side virtualization takes real resources. CPU, a multi-core processor with virtualization extensions, like Intel VTX or AMD. RAM, more is better, since each VM needs its own allocation, say an 8GB host plus 2GB per VM. Storage, a large SSD is preferred for faster VM load times, since each VM is stored as a file that can run 10 to 40 plus gigabytes. And networking, configurable as bridged, NAT, or host-only depending on the use case. Memory directly affects VM performance. Too little RAM and VMs start swapping to disk, tanking performance. Enough RAM, and each VM runs smoothly without dragging down the host. Best practice. Plan your allocation carefully. Say a 16GB host, allocating 4 to 6 GB to VMs, while keeping some free for the host OS itself. Traditional VMs each run a full OS plus apps, heavier on resources, with strong isolation but slower startup. Containers, like Docker or Kubernetes, share the host OS kernel instead. Lightweight and fast to start, ideal for microservices and cloud-native apps. The benefits of containers: lower overhead, faster deployment and scaling, and a consistent environment across development, testing, and production. Here's what this lesson covers. Hypervisors, uses for virtualization, virtualization resource requirements, and virtualization security requirements. A hypervisor lets a computer run multiple operating systems on one system, managing virtual machines by emulating hardware. There are two main types. Type 2, host-based, installed on top of an existing host OS, and Type 1, bare metal, installed directly onto hardware. Here's the structural difference laid out visually. Notice how a Type 1 hypervisor sits directly between the hardware and the virtual machines, while a Type 2 hypervisor has a full host operating system in between. Virtualization shows up in several forms. Client-side virtualization covers sandboxing, legacy support, cross-platform use, like running Linux inside Windows, and training in labs. Server-side virtualization lets one physical server run many virtual servers, for cost savings and scalability. Desktop virtualization hosts virtual desktops on a server, accessed remotely through VDI or thin clients. Application virtualization runs apps in a virtual layer without a full OS install. And container virtualization is lightweight, sharing the host OS kernel. Virtualization resource requirements come down to four things: CPU with virtualization extensions, system memory for each OS guest, mass storage for each OS guest, and networking for communication between VMs, the host, and other hosts. Time for an activity: virtualization setup and resource planning. Review the resource requirements: CPU, memory, storage, and networking. Then plan the setup for a workstation that will run 3 virtual machines. The 3 VMs: Windows 10 for legacy software testing, Linux for development, and a sandbox environment for testing new applications. Allocate resources for each VM and justify your choices. Virtualization security spans 3 layers: Guest OS security means patching and updating VMs regularly, using a template or golden image for clean deployment, and isolating untrusted or sandbox VMs from production. Host security matters because the host is a single point of failure. It needs hardening, firewall and antivirus protection, strong authentication, and monitoring for unusual resource usage. And hypervisor security means protecting against VM escape, where an attacker breaks out of a VM into the host, limiting admin access to the management console, and keeping up with vendor patches. Lesson 8.2. Cloud Concepts. This lesson maps to A+2201-201 Objective 4.2, Summarizing Cloud Computing Concepts. By the end of this lesson, you should be able to answer: what key characteristics distinguish cloud computing from traditional on-premises IT infrastructure? Which cloud deployment model would you recommend for a company needing high availability and data security, and why? And how can infrastructure as a service and software as a service benefit a company in terms of resource provisioning and software development? Two related topics here. First, cloud file storage. Services like OneDrive, Dropbox, iCloud, and Google Drive let you access files from any device, collaborate on documents in real time, and rely on automatic backup for data protection, all while staying in sync across Windows, macOS, iOS, and Android, and scaling as your storage needs grow. Second, the IETF's software-defined networking model splits network function into three layers. The application layer sets policies and business logic, the control layer holds centralized intelligence and makes decisions, and the infrastructure layer, the physical switches and routers, simply forwards traffic based on what the control layer tells it to do. Cloud computing has 5 defining characteristics compared to on-premises IT. On-demand self-service means provisioning resources without human intervention. Broad network access means it's available anywhere over the internet. Resource pooling means shared infrastructure across multiple tenants. Rapid elasticity means scaling up or down quickly. And measured service means a pay-as-you-go model, where usage is metered. Keep those 5 characteristics in mind as we move into deployment models next. On-demand self-service, broad network access, resource pooling, rapid elasticity, and measured service are exactly what shape how public, private, community, and hybrid clouds each get used. Infrastructure as a Service, or IaaS, gives you virtual servers, storage, and networking on demand, with developers controlling the OS and apps, good for custom software development. Software as a Service, or SaaS, gives you ready-to-use apps, like Office 365 or Salesforce, with automatic updates and no local install needed, ideal for day-to-day business operations. Cloud file storage services like OneDrive, Dropbox, iCloud, and Google Drive offer real advantages. File synchronization, so you can access the same file across devices. Real-time multi-user collaboration. Version control, so you can roll back to earlier versions. Redundancy and backup, since the provider ensures data durability. And cross-platform access, working across Windows, macOS, iOS, Android, and the web. Software-defined networking, as defined by the IETF, breaks into 3 layers. The application layer defines network requirements, apps requesting bandwidth, or QoS. The control layer translates those requirements into policies and manages traffic flow, using controllers like OpenFlow. And the infrastructure layer, or data plane, is the physical and virtual switches and routers that actually forward the packets. Here's what this lesson covers: cloud characteristics, common cloud deployment models, common cloud service models, and cloud file storage. Cloud characteristics in more detail. On-demand self-service lets users provision VMs and storage automatically, without IT stepping in. Broad network access means services reach any device, anywhere. Metered utilization means you pay only for what you use: CPU, storage, bandwidth. Resource pooling means data center hardware is shared across many customers. And high availability with rapid elasticity means resources scale automatically with demand. There are 4 common cloud deployment models. Public cloud, or multi-tenancy, is offered by a third-party provider over the internet, with resources shared among customers. Private cloud is dedicated to one organization, offering greater security and control. Community cloud is shared by several organizations with common goals, like compliance or research. And hybrid cloud combines public, private, or community models, letting data and workloads move between environments. Time for an activity. Cloud deployment model selection. Evaluate the 4 deployment models: public, private, community, and hybrid. Then recommend the most suitable one for the organization, justifying your choice based on security, cost, and scalability. There are 4 common cloud service models. Infrastructure as a Service, where organizations provision and manage their own IT resources. Software as a Service, applications delivered over the internet by subscription. Platform as a Service, a development environment with the infrastructure included. And Desktop as a Service, virtual desktops delivered to end users over the internet. In more detail, IaaS provisions, servers, storage, and networking. Think Amazon EC2, Azure VMs, or Google Compute Engine. SaaS delivers subscription-based applications over the internet. Microsoft 365, Google Workspace, Dropbox, Salesforce. PaaS provides development environments and frameworks. Google App Engine, Azure App Service, Heroku. And DaaS hosts virtual desktops in the cloud. Amazon Workspaces, Citrix Virtual Apps and Desktops, VMware Horizon Cloud. Cloud file storage is a type of SaaS that lets users store and sync files across many devices. Its advantages: automated file syncing, real-time collaboration on shared documents, fast and reliable access, and a range of cost tiers from free to subscription. The major players: Microsoft OneDrive, Google Drive, Apple iCloud, and Dropbox. To wrap up Module 8, a solid understanding of client-side virtualization is essential to keeping environments efficient and secure for every user. Cloud computing offers real benefits that set it apart from traditional on-premises IT infrastructure. And every IT professional needs to be able to evaluate different cloud deployment models and service models to find the right fit for a company's needs.